Welcome back. All right, so voltage as electric potential difference. Now, if you have gone into physics, my assumption here is that you have some background from kind of grade 11-ish, and you're now heading over on the grade 12 side, and you're trying to figure out what this voltage and how it relates back, in particular, to the electric field. Now, in the foundational study, where you're going into just studying circuits, you maybe have introduced yourself to voltage. Now, I'll put up a link up above there. That's kind of a grade 11 link. And I will talk about something similar in this video. However, I'm going to extend it so that you can tie back in the electric potential energies. And then, we introduce this word, okay, new voltage, because it's now not for a particular charge, it is for a unit charge, okay? So let's take a look and dive in. So the first thing that you see here on the screen is the electric potential energy difference that you have. And I have talked about this for particular charges, both positive and negative, okay? Again, so a link up above there, and you should be familiar with that. Now, if you've seen that video, you will notice that this looks very similar. Now, I'm going to kind of go back in, okay, on the right-hand side, and I'm going to talk about potential energy now with respect to gravity first, to then jump back over, okay, to the charges and the electric world, and then, of course, how they're tying in, and then you'll see that this voltage is really nothing special, okay, that you have. The only problem is that we use voltage for electric potential, we use it for electric potential difference, so that is something unfortunately you're going to have headaches with. All right, so jumping on the right hand side, so if you have a mass, we know that for this particular mass, we can obtain a certain amount of gravitational potential energy. Right here is at some particular height from the Earth or from some reference. It doesn't have to be from the Earth. Okay, it's always with respect to some reference. So let's call this height h. And we know that this has a certain amount of gravitational potential energy. And we can say this is mass times gravity times the height that it is located in. Now, if that is at that particular instant, okay, in time and position, so where it's located, so let's say we're holding that mass up there, that's how much potential energy that it would have. Now, if you wanted to have it per mass, okay, so per unit mass, instead of having the amount of energy for that particular mass, but if we wanted to know it for any mass possible, then what we could do is the following. We could say that we wanted to know what is the actual, okay, energy per unit of mass. So if we divided this by this particular mass m, then what we would get is within here we would have a certain amount of energy, so let's say it would be in joules, and then we would have it per kilogram if it was for a unit mass, and let's say if it was in metric standard units. So if we divided it by mass, then what we would see is that our equation, mass times gravity times height, it would only be dependent on gravity and then the actual height or distance, okay, that it is located at. So this right here should be very understandable to you. All right, so I have a certain amount of energy, okay, per unit of mass. If you now jump over on the side of charges, we can do exactly the same thing. So sure, we can say that, okay, well, this particular charge right here, it may have a certain amount of potential energy that we would have, and that potential energy that it would have right here for that charge, if you were working this out, would have been the amount of energy, let's say this is the electric potential that it has, at that particular point with respect to the electric field, which is pointing downwards from the positive to the negative, and we're assuming that it's uniform. Now, if you wanted to do exactly the same thing and say, oh, but what if instead I didn't want to know how much energy that particular charge had? I wanted to know what it was per unit charge. So I can do exactly the same thing as I did over here, which is now divided by the charge, not the mass, but because we're not talking about gravity, we're talking about per charge. And if you do this, well, this is actually the electric potential. So on this side over here, so if we were talking about this was the gravitation potential. So with respect to gravity, what was the potential amount of energy per unit mass? On the left-hand side, we have the electric potential. How much energy we have with respect to the electric field that is present, okay, per unit charge instead of per unit mass on the other side. And this is, so this electric potential that we have, so we call this the electric potential. That is what it's called, and we've actually defined it as volts. So volts is equal to the amount of potential energy at a particular point in an electric field, okay, divided by a unit charge. So that's what we would have, and that is electric potential, or in other words, we can use these two words interchangeably. It is also known as voltage. And for this, you can see that the units, because you have joules divided by energy, which would be divided by charge, which would be in coulombs, at least in metric standards. So this right here was joules per coulomb, or in other words, well, joules, don't forget, okay, this is also Newton meters, that comes from work. So remember, work was the amount of force, okay, and then the displacement that you had, so Newton meters divided by coulomb. So these two are interchangeable. And now, so kind of going way, way back, I think it was around 1800 or something like that. Don't quote me on it, or don't reference me on that. You may want to look it up. But the scientist Volta, okay, which was an Italian scientist, worked, okay, and he actually kind of made up, at least from what I know, is one of the first batteries. And Volta, okay, was a scientist which was working, okay, on these batteries and has come across through voltages and so on. And now in kind of recognition of him, we mention and we state that we have joules per coulomb, or Newton meters per coulomb, is defined as the volt, okay? So this is the volt, which is a single unit, okay? So 1 unit, so 1 volt is equivalent to 1 joules per coulomb, right? So that would be the amount of energy that you would have, in this case potential energy, for every single coulomb that would pass by, okay, in terms of charge. So that is where volt comes from. Now, I know it's going to be annoying for you because within here we have voltage, okay, which we just said is electric potential per charge. So that is voltage. And we also use V, okay, for volt. But hopefully you can distinguish between the unit and the actual quantity itself. Of course, this is just a quantity, something that we can measure, and it is related to the electric potential. So that is per charge. Now, before, we were just talking about electric potential, period. For a charge, how much does it have? Meaning, how much energy does that thing carry when it is right here? So you know that if it's, say, if it was a positive charge, okay, it would have a certain amount of potential energy, and then it can be pushed down, okay, and it can have a potential difference, okay? So that brings us to the next kind of idea and topic. So as you are talking about this voltage, which is the electric potential at a particular point in an electric field, you may want to think about the actual electric potential difference. Now, we've heard this, right? So within here, so if I scroll back up here, this is exactly what we had over here. Now, I'm going to kind of copy this and duplicate it and bring it down here for us so that we can see this. So recall that this symbol right here meant that we have a change in electric potential energy. So there's a change or a difference, which we called, or at least I have called, also the electric potential difference. And what did that mean? Well, what it meant was how much work you would need to do on this particular charge, or at least how much the electric field would do if you kind of moved it from one point to another. So you have some initial amount of electric potential energy, so that might be up on top. And then as you bring it down to another point, it will have a different amount of electric potential energy at that point. And between these two, so we have a difference, right? So how much work that we would need within here. This negative is just with respect to a positive charge. Again, you can go back to that link if you forgot. And this right here we've defined as simply the negative. So whatever the charge is, this is the electric field, and this is the displacement, and that will be the displacement right here, okay, in between as you move this charge from one point to another. And that was called the actual difference in the electric potential energy, which we can call the electric potential difference. Now, that electric potential difference, notice that right here we said that the electric potential, this is at a point, is called voltage. Now, we can have a change in voltage. So if right here we have changed this from one point to another, so we certainly can find out what the difference is. So that would be the difference of the electric potential energy that you have. But if you take this and now you divide it by Q, that would be the change in voltage, or the difference in voltage that you have. So this right here, if we wanted to take this and now say, all right, we can define the change in voltage. And that change in voltage is nothing else but the change in the electric potential energy. So that's the difference divided by the charge. So that would be between one point and another. So now you know what the difference is between one point and another. And in fact, when you are studying circuits, so if you have a circuit, and let's say you have a battery, and this is 10 volts, okay, so really what you are saying is, okay, so as you have a plus and a minus within here, this 10 volts, this voltage, really is the change, okay, in voltage. That is what exactly you are doing when you are dealing with circuits. And what it tells us is that, so for example, if it was 10, that would mean that this would be 10 joules of energy, okay, that it would take, so that's the amount of work that you would need to do for every single coulomb to move that charge from one point to another through the circuit. And if you have, for example, a resistor, okay, and let's say the resistor is 10 ohms, okay, so what you would have, you can then calculate, okay, the voltage across that. And then that's how much energy you would need to go over that resistor. And then that resistor, okay, you would have, let's say, maybe 10 joules of energy, okay, per every single coulomb. Okay, so that's the voltage right there. So that is how much work. Now, where would that go? Okay, it would dissipate, okay, most primarily into something like heat or thermal energy, okay? So you would have that in resistors. So that's when we say voltage, okay, we very often, when we're studying this and we're talking about electric fields, we can talk about the electric potential as a voltage that is at a particular point, but we can also say the voltage difference. But that difference, the word difference, we don't really use. So we often say voltage at a point, or a voltage which is across, okay, between 2 points from an electric field, from one point to another. So in summary within here, so this right here, okay, is called the voltage difference, or the difference in the voltage between two particular points in an electric field. And it is also known as the electric potential difference. Okay, so that is, again, something that you're going to have a problem with as a student, because you're seeing this electric potential difference, okay, in so many different places. Remember, this electric potential is the voltage. This difference, okay, is this symbol right here. And we typically put the symbol in front, just like we would for any other quantity. And that is still, okay, sometimes called simply voltage for short. It's way more convenient than calling it electric potential difference every single time. And it has exactly the same unit, so it's joules per coulomb that you have, okay, as you're going through. Now, within these voltages, so something that you should be aware of. If you do take this equation, so I'm going to just copy this out. And if we take this, okay, so right here, notice what this will simplify to. So this is known as the voltage, okay, difference, okay, within here. But this right here, well, we know what that is. This is just negative Q, okay, this is your electric field. So that we have, again, we'll assume that it's uniform. And this is delta D, right? So that is coming in just straight from the formula that we have. And now you're dividing by Q. So this Q cancels out. And what that tells us is, oh, that the change in voltage is nothing else but the electric field. Okay, so the strength of the electric field, so the magnitude, times the displacement that you have in between the 2 points of interest. And when you multiply these out, okay, together, you're going to get what the voltage difference is. Now, this negative symbol is there, kind of, it's annoying to have it there, but it is there because we typically define it with respect to a positive charge, right? So if you know in which direction the electric field points, then, you know, if it goes from positive to negative as a definition, okay, then you know what that direction is, right? Now, in terms of a voltage, as you're going through, it's going to go from a positive to a negative. That would be on the positive side. And if you go from a negative to a positive, okay, it will be on the negative side. So this equation is a pretty useful equation for us to be able to have. What does this equation also tell us? Well, the equation tells us that we can actually find the electric field if someone tells us what the voltage is, or the voltage kind of difference, the electric potential difference is, okay? And this would be divided by delta D right here, you know, the negative symbol, okay, as you're going through. Again, the negative, okay, would be, remember that the electric field just tells you from which way it is pointing, right? So from high potential to low potential, okay, energy that you have within it. So that is pretty interesting for us to be able to have. So we have defined a few things here, right? We have defined what voltage is, which is the electric potential. So that is going back to here. This happens at a particular point. So how much potential does it have per charge? So that is voltage. We have defined also the difference between 2 points. This is delta V. If you're going to be dividing, okay, the amount of electric potential energy it has, so the difference between it by charge, that would be your difference in voltage, or the electric potential difference. And because we have that, we can then take the formula and then substitute this back in where the charges will cancel. And we find out a very nice formula for the electric potential difference, or just for the voltage itself. And then if you want to rearrange this, you can certainly find out the electric field if you know what the voltage is across a certain displacement. So these are all super useful. Now, just to kind of complete this, please note and recall that the units for the electric field, right? The units for the electric field were newtons per coulomb, right? So that was the strength. So how much force you would have per coulomb. That was the unit. But hold on a second. Now you can see from this right here that the unit for voltage, okay, is volts. And then for the displacement that you have would be meters. So these two units, Newton per coulomb, is equivalent to volts per meter. So that is something that you should be aware of, because sometimes it might be written out that the electric field is volts per meter, and sometimes it might be written out as Newton per coulomb. All right, so that is the introduction, okay, to the electric potential difference. That's delta V. Sorry to tell you that delta is often dropped, okay, like it is dropped in circuits. We just write V, but it means actually delta V because it is between 2 points, okay, so that's the change in between there. Okay, so that's what we had defined. as we had introduced this video. All right, thanks for watching. We'll see you in a future video. Happy studying.